in this case x1, y2 minus x2, y1. And if for some reason you don't know the coordinates of the vector, but you only know their length and the angle between them, then that would be length of vector A times length of vector B times sine of the angle. So the cross product is usually used to understand if I have one vector, say A, so and the other vector B is the cross product, the sine of the cross product can be used to understand to which side of the vector A the vector B is, to the left or to the right. So if it's to the left, it's positive. If it's to the right, it's negative. If you use this formula to calculate, and your x's are like x. If you solve the x's like I goes down, y goes down, then the signs of cross product will change. The dot product of these two vectors is like the length of one vector multiplied by the length by the scientific length, again oriented length of the projection of the other vector to this. So like we make this projection and multiply. This is also known as a scalar product in many like algebraic operations with vectors. When you talk about algebraic geometry, the dot product is referred to as scalar product, and its formula is x1, x2 plus y1, y. So we like make pointwise multiplication of coordinates and sum them up. If we, again, for some reason don't know the coordinates of the vectors and only know their length and the angle between them, then it's the product of their length times cosine of the angle between them. Dot product can be used to understand if the vector is like directed forward with respect to another vector or backward. And also the cross product can be used to determine collinearity. The two vectors are collinear if their dot product, if their cross product is 0. Similarly, the dot product can be used to determine orthogonality, like the two vectors are orthogonal if their dot product is 0. So if we draw the total picture like this, so this is vector A, then dependent on the signs of cross and dot products, there are actually 8 possible locations of another vector with respect to vector A. So this area corresponds to positive, so like cross. This area corresponds to both positive. This is negative cross product, positive dot product. This is positive cross, negative dot, and these are both negative. And on the line, blue lines there, which in case of collinear or orthogonal, then there are zeros correspondingly. So it's like 0 plus, plus 0, 0 minus, negative, and negative. So if you want to find the relative position to vectors, then you can use the signs of cross and dot products for this task. If you want to find the angle between two vectors, what you can do is you can use any of those, so you can know coordinates of the vectors. You can calculate the length of the vector is the sum of squares of its coordinates. The square root of them. There is a function for that in C++ called hypo, but I do not recommend using it because it is quite slow. At least it used to be quite slow. Maybe it's fixed now, but it used to be quite slow. So like it's making the manual evaluation of this formula is faster than hypo for some reason. Actually, the reason I don't again know is or was that hypo has some precision restrictions from its definition, so it uses some more complex, like internal calculations. Get the hypo more exact value. I don't know. Maybe it was just like 5 to 10 years ago. So to know the angle, you can like divide the, for example, the cross product by the product of lengths of the vectors, and then we'll get the sine of the angle. Similarly, here you can get the cosine of the angle. The problem is that both sine and cosine have areas of they are very flat, like they both have the same graph, shifted by pi divided by 2. And here it is fine, the inverse function works great, but near the maximum and minimum values, like here, the inverse function has poor precision. So it's better to use the function which is called hn2. hn2 is a special function that takes 2 arguments. They are called y and x in this order for some reason. And it returns the polar angle on the point xy. We have the coordinate system. And you have the point. With some coordinates, probably they can be negative coordinated. Then the function a2 and hn2 returns this polar angle. Well, first of all, it can be used to return polar angle. Of course, we can, for example, get polar angle of AB, subtract them, and get the angle. There is another way to do that. If we take a look, we see that the x coordinate of the polar of the point with the distance from the origin r and polar angle t is r times cosine t, and its y coordinate is r times sine. So if we look again here, we see that these are actually the coordinates, y coordinate and x coordinate of some point at this distance from the origin and the polar angle a. So what we can do is we can use hn2 of a cross b, a dot b, and that would be the angle between the two vectors, and this is quite a precise way to determine that. You can, if you wish, normalize that by dividing that by the product of their length, but it is useless actually because the function itself normalizes its arguments, so no need to do the double work. You can just pass these two values and it will return the angle between the vectors if you need it. It will be a sine angle, if I recall correctly, from minus pi naught to pi inclusive, sine value. And I would not actually rely that minus pi is not inclusive because of the precision issues. Get almost minus pi almost. If it's important for you, then you should take care about when comparing two angles, one of them is pi, another minus pi, almost minus pi, they're actually in the same direction. Okay, so that are the basics. This next thing in the basics is polygons. Polygon, oh no, lines, sorry. The next basically is line. What is a line? There can be several ways to specify the line. We know one way already from yesterday's lecture, but that was the better way because it doesn't work with horizontal, with vertical length. Generally, there are two main ways to work with the length. One is if you have a point on the line and the direction vector of the line, or you can also have the point on the L. And we can also have the point on the line and the orthogonal vector. The line, which is called a normal vector, at least in the question, I don't know. So they're essentially the same. These are essentially the same. We specify the line with the point on it and either its direction vector or its orthogonal vector. In this case, the line doesn't have a unique specification because there are many points on there, and the length of the normal and or direction vector can be also arbitrary. So we have like 2 degrees of freedom and 2 possible parameters that can change. Like one is the position of the point, another is the length of the vector. With the length of the vector, it is easy to get fixed. To fix that, saying that the length of the vector wants to be 1. So this reduces 1 over the possible changes of the parameters. But the point, the change of point, generally are. So alternative way to specify the line would be to give it some called uniform creation, which is a times x plus b times y plus c is 0. Sometimes c is written on the other side of the equation. It's essentially the same. So it's called uniform because multiplying all coefficients a, b, and c by any value gives the same line. So they're actually given up to the constant factor. You can easily get from one representation of the line to another by the following algorithm. So if you have this out, like the point P on the line, and for example, the vector that the direction vector of the line, then the arbitrary point x, y on the line, you have like the vector from P to A cross product to L is 0. And if you write the corresponding variables like x and y here, you will get the formulas for A, B, and C in the uniform equation of the line. And if you want to go back, the normal vector is AB actually, so the line vector is minus BA, which can be easily understood because when you are moving along with minus B, adding minus B to x and A to y, this whole expression changes by 0. And to find some point on the line, well, you can several ways to do that. One way is to guess the point. So let's look very close to this equation and see that the point A divided minus CA divided by A squared plus B squared minus CB divided by A squared plus B squared is on the left. Satisfies this equation. So the idea is just to here and then I don't know if you can remember it, or it can be actually this point is the closest point of the line to the center, to the origin. Coordinate center. So this is another way to find this point. Okay, so the parts of the line are the ray, which is the half of the line, when you are only considering this point, and also the segment, which is between the two points. One idea is that actually you can have also the parametric equation for the line, like A is equal to P plus T times L, like this. And for the line, T is from minus infinity to infinity. For the half line, T is from this. P is the beginning of the half line. T is from 0 to plus infinity. And for the segment, if we use the TA as the vector L, then T is from 0 to 1. So this is a convenient method to define parts of the line. When you're working then with some equations, you're finding, for example, some intersections, you can then just check if the parameter T is inside the required interval, and if it is, then there is an intersection. If it's not, then the lines that contain corresponding objects will intersect, but the object themselves don't. Okay, so now I'm getting to what I also remember, the polygons. I already mentioned polygons. The polygon is given by its usually presented by its vertices, and there is a concept of a polyline, which is just a sequence of segments in each new segment starts where the previous segment ends. And there is a concept of closed polyline, which has the end equal to the beginning, and the polygon is the closed polyline without self-intersections and self-touches. Usually these are the notations. So to keep the polygon, we keep like the vector of its vertices. When you have the polygon, you have actually two traversals of its border, and you can traverse it counterclockwise and traverse it clockwise. The two main problems associated with polygons are find the area of the polygon and check if the point is inside the polygon. To find the area of the polygon, you can use the following way. Take the origin, take the vectors from the origin to all the vertices of the polygon, and let's sum the directed areas of triangles. This is the one of the angles of the directed areas, because it's the one angle triangle, and the second, the other, the opposite side, the opposite leg of the edge of the triangle is the corresponding edge of the polygon. So if you sum the direct areas, then you will the part that is outside of the polygon will cancel out, and the part that is inside the polygon will be counted with the coefficient of 1, given the area of the polygon. So we already mentioned that the cross product is the area of the parallelogram. To get the area of the triangle, you can clearly divide this by 2. So the area is 1/2 of the sum of pi of pi cross pi plus 1 plus 1 1. the area will be positive if we have the counterclockwise traversal on the border of the polygon, and it will be negative if we have the clockwise. It doesn't matter if the origin is inside of the polygon, on the border of the polygon, outside of the polygon. This formula will always give you the area correctly. If you know calculus, actually this formula can surprisingly be improved using calculus so-called green formula. So if you integrate one on the polygon, it's the same as integrate like some functions that the derivative of which partial derivative of which is 1 for one variable and 0 for the other variable along the edge of the polygon. So you do it carefully. But I think that doesn't really matter for us. So talking about the point outside the polygon, this problem is sometimes considered tricky. Let's see. Let's change the polygon. And take some point inside or outside of it. Generally, if you take the point and walk into some direction from this point, you intersect the polygon border several times. If you intersect it the even number of times when the region that was outside of the polygon, if you intersect it odd number of times, then the point originally was inside the polygon. Because the infinity is outside of the polygon, and each time you cross the border, you change the state of being inside or outside. However, the question is, in which direction should we go? Because if we pass through the vertices or walk along the edges, it looks like there can be some confusion. I will give you what I consider the simplest way that doesn't intersect arbitrary half lines or segments or whatever, that only uses cross product and dot product, and doesn't have any precision issues if the point and the polygon vertices are integers. So you take the point and you draw the horizontal half plane to the right. On purpose, I did make this to be the worst looking case, that we have both parts, edges of the polygon and vertices of the polygon on our way. So what we're gonna do now, we're gonna count the number of intersections with non-horizontal edges of the polygon. Horizontal edges are ignored. And for non-horizontal edges, we will consider them half intervals, but not along the traversal of the polygon, but with, for example, the bottom point included and the top point excluded. So if you see, if there is actually closing the border, if you go through the vertex of the polygon, then if there is you're actually closing, crossing the border at this point, then one of these points will be the top point and the other will be the bottom. And if they are both bottom or both top, then you're actually not crossing at this position. So if you go along the traversal, you will always have one beginning and one end of the edge. But what you would like to differentiate between this three situations, actually this and this two. And in this sense, looking at not going along the traversal, but going always from down up, from the lower end to the upper end, gives you the correct count. Horizontal sides can be good. Now talking about how to check if you cross the if this walk to the right crosses the edge of the polygon. So here is the original point A, and there is the edge. So if the edge is totally under or totally above this line, that you definitely do not cross it. So if you have like y min and y max, so if y min is strictly greater, we include the bottom bottom and exclude the top. So strictly greater than y of a or y max is less or equal to y a, then no. We do not add the relationship. Otherwise, it crosses the line. But does it cross the half line that we are watching to the right of the point? The answer is, let's see, if it does, then rotation from the minimum from the lower point to the upper point is counted. If it does not, like I will draw them, if it does not, then the rotation from the lower point to the upper point will be low. And that is when our favorite cross product comes into play. So we just check if, so this is like P minimum, P maximum, if A, P minimum cross A, P maximum is greater than 0. I will not tell you what happens if it is equal to 0, but let's start with greater than 0 then. Plus 1. If it's less than 0, then no plus. What happens if it's 0? If it's 0, that means that this is, these two vectors are collinear, so that means that A is actually on this edge, because it's not there. This condition was already used to check that the line intersects and the line intersects and we have these vectors collinear, so it's not the only. We can do whatever we need in this case. If the points on the border are considered inside, if the points on the border are not considered inside, then it's not inside. Counting can be adjusted like you wish. Either counted or not counted. If it's counted, actually, you will get the outside. If it's not counted, you get the inside. So that's it. Maybe not. No, not correct. If it's it's a separate answer. This is on the edge. You can now counting and not counting. It depends already on the direction of traversal. So if it's along the counterclockwise traversal and up, the counting will give you the inside answer. And if it's the reverse of that, the counting will give you not. But anyway, if it's on the edge, you can make a separate decision on it. So that's it. And if you look closer to this algorithm, it doesn't use any floating point matrix. It doesn't actually intersect anything with anything. So it is very precise and simple linear time. For the general polygon, there is no fast and simple algorithm faster than linear time. To get faster, you need like triangulation and some additional data structures for this, which you wouldn't generally do. But for the convex polygon, there are fast and simple algorithm that we will move right now. If you don't have any questions. Questions for Thomas so far? Yes, please.
How do you detect if the point is on the horizontal edge? Do you have to handle
If
that?
the point is on the horizontal edge, you have to handle that in some way. If you want. If you want to check. So maybe, well, but if the point is not on the edge, the horizontal edge can be completely ignored. The point is on the edge, or can be on the edge by the statement of the program. So you should do something. In this case, you should have some decision that comes from another properties of the program. So you should check for it separately. Checking that the point is on the horizontal edge is actually quite easy. It's horizontal, so it's y mean and y marks are the same. And the x of the point and the axis of the edge. Again, no need to intersect any objects. Okay, then let's move on. The convex, the polygon, well, any set of points is called convex if any segment that connects two of these points consists completely of the points from the set. So for the polygons, the convexity can be checked in the following way. For example, how do you tell that the polygon is convex? Because now, when you make, for example, when you make the counterclockwise traversal of the polygon, you always turn to the left. At some point, turn to the right, then this is the concavity, and the polygon is not convex. If you are given a polygon, that is enough to check. If you are just given a closed polyline, then and they are not guaranteed that it's a polygon, then it's just maybe not enough to check because, for example, like something like that, like this, you always turn to the left, but it is definitely not only not a convex polygon, but it is not a polygon. In this case, you need to count the number of, the total value of the angles that you are turning. So you are turning like this and this and so on. And if it's a polygon, then you turn at 2 pi exactly. If it's not a polygon, then you turn like at this satanic star, like around 4 pi. Or like this 6. So, but you would turn at 2 pi at the total for any polygon, not necessarily convex, because if you make a concavity, then you turn like to the negative value. So you need to check both conditions. That you always turn to the left, and then the sum of the angles that you are turning at is 2 pi. To get the angle at which you are turning, you can use the formula like this. So for the convex polygons, the point localization, that's called point localization problem. Checking whether the point is inside or outside can be made a little bit easier, maybe not easier, but faster. So consider the convex polygon. Let's take the most low point vertex of the polygon, that point with the minimal y coordinate. Problem although there can be actually 2 of those. Let's take the leftmost one. That leftmost bottommost point. If the polygon, it's not very nice to say, like not strictly convex, like 2 consecutive parallel edges, or linear consecutive edges, then there can be more than 1 and even more than 2 bottommost points. Well, again, taking the leftmost, but well, it's a good style for problem centers not to give such situations in the input, like multiple consecutive collinear edges. But I guess some problem centers do that because every time I give some geometry program, there is always the answer and the clarification. Is it possible? So people don't believe that. There are good that generally means that there are bad problems. to make such a change. Okay, so we have taken this other vertices along the traversal of the border of the polygon are ordered now counterclockwise related to this point. The first is the edge of the polygon, it can be horizontal, it can be like not necessarily. There is no necessary. It's not necessary that there is a horizontal side, but there can be. We have our plane divided into like this segments with the vectors to the points, the vertices of the polygon. And to make a point localization, the first thing you do is you make a binary search to find out in which sector the point in question is. So to make the binary search, you need to compare two angles. Like, for example, you have like the vector to your point in question, A, and you have the current middle point in the segment of the binary search. And to compare them and to understand to which side should we move our ends of the binary search segment, we use relative position of the vectors. So if from A to M we go counterclockwise, so the cross product is positive, then we should move R to M. If it is the reverse situation, then we move L to M. So in the end, we will have L here and R here, and we only need to check if the point A is inside the triangle formed by this lower point, point with the index L and point with the index R. Checking that the point inside the triangle can be made either by this algorithm. This time it is constant time because the triangle has 3 edges. Or, for example, another algorithm that you can do is well, you can also check, for example, that LA is to the left of LR, like this, because it because. No, I don't think. Or is it the correct? I think yes, it's correct. But
point like outside, but
if it's the point that's outside,
but on the other side, like, from the other side, like, on the road,
again, where?
like on the road.
Reflected by reflected by O.
There?
Yeah.
Well, if the point is below the bottommost leftmost point, then it's definitely outside of it shouldn't. So you must consider the point is probably checking yes that from LR to LA is counterclockwise is okay. To check if it's inside, if it's guaranteed to be inside this circle.
Like if it's above O there, but on the left, like
Here?
like on the
I don't know. Here again. There it's not again if L is the last value or the last value of then R is definitely outside. It's not on the edges. If it falls into this segment, it is definitely outside. But I wanted to tell you about another way to check if the point inside of the polygon, again not necessarily convex. another thing that you can do is you can look at all the angles that the edges of the polygon, this time in some traversal, for example, counterclockwise, make from this point. So this angle plus this angle, remember that we must always use direct angles, of course, with the sine. Like that. So if the point is inside, then the sum of these angles will be 2 pi. If the point is outside, then the sum of these angles will be 0. I don't like this method a lot for general polygons. For me, the way with making this outline to the right seems more stable because we only use integer arithmetics. Although, since we are comparing 0 and 2 pi, which are quite far apart, so maybe the precision losses to get 5 precision losses must have very many. But for the triangles, since we only have like 3 angles, this may be the good, also the good way, and then can fit into 1. Well, so this gives us after, if you have like the polygon first and then you have wires at the points, then after reading the polygon which takes n, you can answer wires and log n. So, well, the next thing about convex polygons and convexity in common is a convex hull. We have discussed it a little bit yesterday in the context of the hull of the lines. But let's revise it briefly. The convex hull is the minimum convex polygon that contains all the given points. Okay, it can also be seen for any set of points. This is the intersection of all convex sets that contain all these points. The intersection of convex sets is definitely a convex set itself. So this is the correct definition. For the case of finite number of points, the convex hull is always a polygon with vertices in some of these points, and it can be found using different algorithms. There are actually the very simple and efficient algorithm is n log n algorithm called graph algorithm. There are other algorithms actually. There is so-called Jarvis algorithm that is n squared in the worst time, but it's actually n times the number of points of the convex hull, which can sometimes be okay when you need, for example, to make so-called onion decomposition. Onion decomposition is when you make convex hull, remove it, again make convex hull, remove it, and so on. If you use Graham, it will be n squared logarithm n, but with Jarvis algorithm, that would be n squared because every point is only the one layer of that onion convex hull. And it can be proved that in general, if the points are given to you as input, that you cannot find the convex hull faster than n logarithm h, n logarithm h is the number of points on the convex hull. There are several algorithms that reach this. Symptotics, but it's generally for the purpose of programming purposes, it's not relevant because logarithm n and logarithm h, they are identical from all points of view except theoretical, but these algorithms are much more complex and are not worth coding in the code. So Graham algorithm, that's like this. It starts with the same as the previous problem, localization. We find the bottommost, leftmost point, and then we sort all the points that we have with respect to the angle to that point. In such sorting, we can use cross product as the comparator because it's transitive if all the points are in the half plane. By the way, make this note if you remind that when sorting vectors from the point, for example, counterclockwise, in general, you cannot use cross product to compare any two vectors just like operator because it's not transitive. So this is positive, positive, positive. It's a very common bug actually. So what you need to do is to separately sort, for example, upper half plane and lower half plane and unite them. So this is the same way to deal with that. You can create a single comparator that initially compares if it's upper half plane or lower half planes, and for example, lower half plane always goes before the upper, and if they're both in the same, then it's in fact cross product for comparison. But it has sometimes some issues with horizontal vectors. So what I usually prefer to do is to make separate arrays of vectors, one for the upper half plane and positive direction, for example. If it's horizontal, another for negative. Well, if you want from minus pi to pi, then negative must go to the upper half plane and positive direction will go to the lower. And then sort them separately using just a simple cross product operator, and then turn them back. This is what I do. Question?
N-squared instead of n-squared logging with Raven, since the n-logging part is just sorting.
Yes and no, but this point will be dropped away. You must search the new lower left. Don't feel that the sorting order can be preserved.
Isn't like the same sort by y and by x?
I don't feel well. I don't feel that it is true what you're saying. Maybe, but it must be considered separate. Well, I know that if you must sort by angle from the lower. If you sort by some other comparator, I don't think that the found this one. Okay, so let's get back to graph one. So you sort according to the direction of this point to the opposite point, and then okay. It should have been yesterday that the algorithm for the lower half of the lines is similar to this one, because this one is more basic. But since we are doing them in the reverse order, it's similar to the stack algorithm that we were using yesterday for the lower half of lines. Just a little simpler, because we don't need to intersect anything. We go with the stack, and what we check if the condition that we're checking for the convexity of the polynomial. So if we turn to the left for the next point, then we push it to the stack. If we turn to the right, then we put this on the stack. It's not on the convex half. Now we're moving to the left, so we keep again this turn to the left, keep turn to the right. Remove. Turn to the left. Turn to the left. Turn to the left. If there are collinear vectors, then you should sort the points by increasing of their distance along this vector by increasing of their distance from the origin point from the left, bottommost left point. In this case, it would go like this. So if first go here, then it will see that we are going to the right. It will remove this both here. Then it's again turn to the right. It will remove this and go here. So this will automatically be okay. So that's it. That's Graham's algorithm. Sorting, yes, you are correct in the sense that a logarithm n comes from sorting, but I don't feel that when making island decomposition, if you remember the output convex hull, one should be the convex hull of the rest of the points, the sorting order would preserve.
I confused with one of them. I confused.
What so? I feel that it will not be preserved, so you need to resource. So the island decomposition with graphic square logarithm. Upper hull, lower hull algorithm maybe can't be used. Okay, so now let's move on. So the next usage of binary search that we will consider is extreme point in some direction. So consider some points on the plane. They are given as a and the question is, the query is, you're given a vector which specifies the direction, and you want to find the extreme point in the direction. This can also be viewed as some flashback from yesterday. If you remember lambda optimization, we were moving the line from the minus infinity until it hit one of our points on that graph. So here is the same. We take like the line and look at the minus infinity and move it in the direction orthogonal to that line until it hits one of the points from this is the minimum point in this direction, and the last point that we hit is the maximum. So what we want to do is to find the extreme point in the some direction. So the first thing is that the extreme point in the direction is definitely on the convex hull. So we build the convex hull. The points inside are never extreme in some direction, and that is, by the way, why the lambda optimization doesn't work if the dynamic programming function is not convex with the connection to the like cost dependent on the number of patches. So now what you want to do is you want to find the extreme points in these directions. It can be seen that this is the same as maximizing and or minimizing if I dot L direction L and dot. So this is the projection. This is the length divided by length of this. So this is the projection product of this length by its length by the this is the product of not divided. Wait, not divided, just like this. Because this is the product of the length of L times the length, directed length of the projection of OPI to L. Like, let's say, length with the sense that it is signed length. Signed length. Yes. So if we take like this, that would be like this minimal possible, and for the extreme max, this would be the projection would be the maximum. Let's see how this function behaves along the convex hull. So that depends on where we start. So if we start at some point, like 0, 1, and so on, h minus 1. When we start at some point, then it will usually, like in this example, it will go down to the minimum value, then up to the maximum value, and then when we cycle is over, it will go back to the original. So this is the graph of the function. The x is the number of the point along the convex hull, like 0, 1, 2, 3, 5, 6. And the y-axis is the value of our function. So this is called like sine-like function. So it's descending, descending. Or it can be the opposite. Like if we start here, it is ascending, descending, descending. That depends on when we start, and we cannot make sure where we start because the direction is required. So, how can we find the extreme point of direction? We use binary search, but we must take a careful look at what is the condition. How do we say at which side of the current point that we analyze the answer, for example, the minimum point is. To check that, we use the following. So let's see. We have, and we don't know which of this we have. Again, we have either. Let's say that for the initial point is like 0. So we either have this, or, and we don't know which is the situation. If we start here, we have like. Our goal is to find the minimum point. So, the solution is the following. So, first you check if you start with ascending or ascending, and if you start with ascending, for example, you can change the direction to the reverse, and minimum and maximum just exchange. So you then exchange the back. So we consider the general case that we start with descent. Then if we are consider that we take some point M in our binary search and we want to understand what to move, R or L. If we are ascending and we start by descending, then we are definitely after the minimum already, so we should move R. But if we are descending, it depends. If we can be here, and then in this case we should move L, or we can be here, and in this case we should move R. How can we distinguish between these two situations? The answer is now we compare not the direction of changing of the function, but the value of the function. The value is less than the original value that we used as a 0. So for descending, if value is less than value 0, then the 0 value, then we are here, so we move L. If value is greater than value 0, then we move R. So this allows us to use the binary search for the sine-like function, and in this example, this is the projection of the position of the vertex of our convex hull to the given vector. This gives us extreme minimum and extreme maximum for the current direction. There is another example of a sign log function and binary search in it. It's when you want to put the tangent from the point to the polygon. You may be used to putting it to get finding the tangent from the point to the circle, which can be used with given explicit formula. Which can be done using explicit formula. But for the point, putting a tangent from the point to the polygon, we actually see that this is the same situation as with the extreme point in some direction. If we look at the angles from let's sum of the point is the zeroth point, the initial point of curve. So let's look at the angle between the vector from the tangent point to the point number 0. So there, as in this example, they again start being negative, then they start being positive again, and then they start being negative. So we get approximately the same situation, but from a little bit different setting. So we have the function that starts with 0, goes down, goes up, and then again goes down, back to 0. So to make the tangent from the point to the polygon, you must again find this minimum and maximum value, which can be used using the same binary search. That's for the extreme points in some function. Okay. Sim a little bit. I don't know. Sleepy maybe. Okay, questions for fun? Comments? What's with our time? 9:45. Do you want a coffee break or do you want another element? Bad question. Let's what's the question?
So I didn't understand why evaluating the value only.
You see, let's see. So you have the function that behaves like this. So it starts with 0, goes down to some minimum value, goes up to some maximum value, and then goes back to 0. This function, in this case, is this product, which is actually just this easy to calculate. And in this case, it's like a P0 press a Pi. It also behaves like this. So you want to find the minimum value, you use binary search. So it's L bar. You take M, and you want to understand at which part of the graph you are, so you have to understand what are you moving. If you are at the increasing part of the graph, you are definitely to the right of the answer, which is the minimum, maximum symmetry. So in this case, you move R. If you are descending, then you can be either before or after, depending on are you under the 0 value, which is the value of the first one, or before, or above. If you are under, then you're on this slope on the descending part, and then you move L. If you are here, then you move R. At this graph, it looks like, well, it is like a true sine function, but this can be sort of very much like it, like this. And that's why you cannot look at the values of M itself, you must look at the values of the function that you're on. Your question?
In this function to achieve the maximum,
you can also do a ternary search.
The problem with ternary search is that the function is not like convex, it's not concave, so it's like a sine form. So if you can find the zero and on this part and on this part, the ternary search that is you can do. But how do you find this? What 0 point? It can be found using similar binary search, but if you're already using binary search, then let's find what we are looking for. Why would we find some auxiliary point and then use ternary search? I have two algorithms. Another question?
Yeah, just like an increment. Like, if you check if you are descending or you are ascending, will you just compare like
Yes.
the next value?
Just compare with the next value, yes.
And
Well, yeah.
yeah, there's no simpler way, right? Like,
In general case, no. Maybe in some cases you can. But I would just compare. In particular, for example, projection to some direction, you can actually, instead of comparing two values, you can compare the. You can calculate the pi plus 1 dot L and compare it to 0 to see if you're going along L to the next point or against L. But it's approximately the same number. Okay, let's then make a quick break and then get back to some more advanced stuff.
Yes.
Guarda, dai, sono. I think the size was there, but I'm not sure that's
Right.
yeah.
Okay, so let's move on the final part of the final lecture of this week. So let's move on, and our next part of the lecture will be devoted to randomized algorithms and geometry programs. So what are we were gonna consider 3 algorithms actually. 2 of them are really useful. Well, really useful is relative, of course, because if you don't have this problem to solve, it's not easy. Yeah. But the third one we will consider, and then consider even more simple algorithm. So okay, let's consider the following problem. We have points on the plane, and our task is now to find the circle of the minimum radius to cover all the given points. This problem is sometimes referred to as min disk problem. So the minimum disk containing all the given points. The naive algorithm is the following. So it's clear that you can like do the following. Start with a very, very big disk that contains all the points, and start shrinking slowly. Like the points can be interpreted as like nails into the plane, and they prevent it from shrinking too much. And what will finally stop our disk? There are 2 options. Either it is the circumference of 3 points like this. In this case, this is the acute triangle. Or there can be a triangle like this, and in this case, the longest side will be the diameter of it. So, a simple algorithm that runs in n to the power of 4 is to iterate over all triples and all pairs and check if the triple is okay or if the pair is okay. What we will do now, we will modify this algorithm to run in linear time using randomization. So, how will our algorithm work? Let's randomly rearrange our points. Let's random shuffle them. And do the following. The algorithm runs like this. So, suppose that you have your n points, and you have them in disk for n minus 1 points, with indices from 0 to n minus 1. Let's look at the point number n. What is the probability that this point is not inside the min disk for the n minus 1 first point? It's actually quite low, because with the random shuffle we can talk, it is correct to talk about the probability. Yeah. So the only option that this is not inside the min disk for the previous n minus 1 points is that it is either one of these 2 points, the ends of the diameter, or one of these 3 points of the triangle, so that this is its circumference. In both cases, the probability that the last point is one of those doesn't exceed 3 divided by n. So it's quite low. Okay, how can we do this? Let's try doing like this. So, I will call this function solve 0. Solve 0 means that we know 0 points on the that definitely belong to the circumference, so that are on the edge of the mean disk. So 0 will be, we don't know any point yet on this edge. So what do we do? Again, outside of this, also, we have randomly shuffled our points, and now their order is random compared to 2. So we go. So what for example, for the first 2 points, it's easy to find the mean disk if we just put it as one diameter. So let's start with that. So the circle is circle on P0 and P1. Then we go through other vertices for I from 2 to n minus 1, and we see if Pi is inside C. It's easy to check if the point is inside the circle. You just do what? Check if the distance to the center is less or equal to the radius. Yeah? So if Pi is inside C, we don't do anything. It's okay. The invariant is that C is the mean disk for the first points up to point number I. So to keep the invariant, that case if Pi is not inside C. In this case, we need to adjust RC. But what do we know from the argument, from the previous argument? We know that this point must definitely be on the border of the disk, so on the circle. So in this case, C is, we will solve 1 for I. What does it mean? Solve 1 will be the additional function, the help function that will find the mean disk of the first I points, knowing that the point number I is on the border of the circle. How does solve 1 work? How does solve 1 work? Okay, so now we have the first I points. Let's start with the circumference of P0 and Pi. And let's try to fit all the other points inside. So for J from 1 to I minus 1, we compare it at the end, return C. So for solve 1, now, if Pj is inside current C, then it's okay. If Pj is outside of the current circle, then there's a problem. But in this case, what we know? We don't know already 2 points on the border of the circle. That's Pi and Pj. So if Pj is not inside C, then C is solve 2 for I and J. Solve 2 for I and J, and in the end return C. Solve 2 will find the main disk for the first J points and point I, with between J and I are not considering that. Knowing that I and J must be on the border of the set. So how does solve 2 work? We start with the circle on Pi and Pj, and you know that so far we didn't need to put the circle on 3 points, but unfortunately this could not be forever. Sooner or later we should have done this, and this is the point where we should do this. For k from 0 to j minus 1, if the point pk is not inside C, then C is replaced with a circle now on 3 points. Pi, Pj, and Pk. Well, we could have way to solve 3 knowing 3 points on the circumference, but be just the same as just to create the circle. So how to create the circumference of 3 points? Here we have the points. What we do? We make a perpendicular to the segment from I to J, perpendicular to the center of the JK, and the intersection is the center of the circle. So what you need is you need to find the center of the segment. This is just the average of for both coordinates. You need to find the perpendicularity is also easy. We see that the normal vector, we just for AB, the perpendicular is minus BA. And we need to intersect 2 lines that I will leave you as steps. Section 2 lines, I think, is one of the best known geometry primitives. So, we have 2 questions. 2 questions are: why does this algorithm work, and how long does it? Question?
For me, it's not obvious that when you recalculate C to be the circle on the I to J, it considers to.
Yes, absolutely. That is the first question. I said that we have 2 questions left. Why does this algorithm work? How long? What is its time complex? Okay. So the first question is, why does this algorithm work? The answer is these functions solve 0 in suppose the invariant is suppose that solve 1 correctly returns the minimum circumference of the first I points, given that its border, its circumference contains the point I. Then solve 0 must work. Solve 1, unlike solve 0, cannot be used directly. You cannot call solve 1 for any point I. You can only call it for such point that it is known from some other observations that the point Bi is on this border. If you call it for arbitrary points, it may not work correctly. For example, the point I is inside, it always tries to keep it on the outside, and this replacement can spoil like something. So again, solve 2, answering to your question and the general question why it works. Solve 2 cannot be called with any 2 indices. It can only be called with such 2 indices of points that it is known from some other observations that they are on the circumference of the correct solution. So that's why this replacement of the circle here works, because we know that I and J are on the border, and the previous circle didn't contain K, so K must also be on the border. And since we know 3 points on the border, we know that the main feature here is again that solve 1 and solve 2 cannot be used outside of the algorithm. They cannot accept arbitrary points as argument. They can only accept correct points. So the invariant must be satisfied that these 1 or 2 corresponding points are on the order of the answer. If this is the case, then they must work because they have no chance not to work. How can it not work? Now, well, I understand that this still may not be completely clear, but okay, we'll have to go through that. Maybe it takes some time to settle in your mind. But now let's see what the time complexity is anyway. The time complexity for solve 2 is clearly all J. J, the minimum of the J. Okay, what's the time complexity of solve one? We have I iterations. If is not satisfied, it's constant time for that iteration. If is satisfied, if J is not fancy, then we add J. But the probability that this happens is if among the first J points, the last one, which is number J, is one of the points that are on the circumference. One is almost already known as I, so 2 or 1 remains. Almost 2 divided by J is the probability that J is on the edge of the border, and so 2 divided by J times J plus 1 is on average 1. And the similar argument here, so it's O1 on average for one iteration and OI for all iterations, and therefore here the same argument 3 divided by I times I plus 1 with O1 per iteration and O n on average. And the random shuffle can also be done in linear time, so we get the linear time algorithm on average, and it really works fast. It's very difficult to make it work slow actually, because yes, we have evaluated only the average time, the variance we have not evaluated, but you can guess that the variance cannot be extremely big. Yes? Probably it would walk fast more. So this is the idea. The main disk is not so very important problem, but it is nice to demonstrate this. And I told you that we will only consider two-dimensional geometry today, but the fact that you can see is that this can generalize actually to have the linear time algorithm for minimal sphere containing the given points in 3D. We will, in that case, we will need another solve 3-1 and like the minimal 4-dimensional flow that contains all the points in the 4-dimensional space and so on. However, the complexity of the dimension is not that good. It's like, I would say, probably some kind of p factorial and like the complexity is good. Like, let's find attention that we have 1, 2, 3, so probably there will be 4 then and so on. So the dimension complexity is exponential, but the point number complexity is linear, independent of the dimension. Of course, this starts to play a role, so pushing the multi-dimensional ball on the number of dimensions plus 1 point, number of points, is not an easy problem as well. You need to intersect like half the plane, so maybe there is another polynomial of D for solving the system of like linear equations to find the center. There is also maybe for large number of dimensions there could be some special cases like we have a special case when it's on the like the diameter for the sphere. There is like the triangle, so you can imagine the sphere here and so on. So I would not be really happy to write a generalized version of this algorithm for arbitrary number of dimensions, because that linear algebra is constant to the first thing. This can also be reduced back to the one-dimensional algorithm, which is a funny way to find minimum and maximum. So you can imagine that the circle is the segment for the one-dimensional. So this is just the ridiculous way to find minimum go along, and if the current point is not inside the current segment, it must be minimum or maximum. So you replace that with the sort1 function. And maybe it would be easier for you to understand why it works for 2-dimensional. I can imagine 1-dimensional. You know the maximum, and the current point is not inside the segment, then extending it to the minimum keeps all the previous points inside the kernel. You can get outside, given that this is definitely the same argument for the side. The question.
The only thing you need to know before solve 0 is that P0 is in the
No, for solve 0 doesn't make any assumptions. The only thing you can do before running solve 0 is to randomly shuffle the points. And again, this is only needed to get the time complexity. This would work anyway, but just it would take like a cubic time if we don't shuffle point in the worst case. Although, again, to make it cubic time, you need to be very careful with introducing the input data, because you need solve1 to be called on a significant number of steps and solve2 to be called on a significant number of steps, which I think is not so easy to create such tests, but I probably. Okay, let's move on. I will give, as I promised, 2 other examples of algorithms that use the same idea. The first one will be the replacement of the algorithm for the 2 closest points, if you remember. 2 closest points. The technique that we will be using is called grid refinement. So, our idea is the following. We want to suppose that we know the answer. We know that the 2 closest points are at the distance d. And there are no points closer than d. What can we do? Divide your whole plane into squares of size d times d, and add the points one by one. For each cell of the size d times d, you keep the list of points inside this cell. Actually, there can be too many points. The same argument that we used for the previous algorithm said that there are at most like 4 points in each cell. Actually, maybe even 3, because definitely that we will like include 2 sides and not include the opposite sides. So fitting 4 points may be difficult, because 4 points must occupy 4 angles, but one of the angles is excluded actually. So probably around 3 points maximum per cell. So after that, what we know the answer. We know that the 2 closest points are at the point distance d, but we need to find those points. How can we do that? We look at the point, here it is, and we look at all points inside this cell and also in like 8 adjacent cells. If this point is one of the 2 closest, then the other one cannot be too far, because it's the distance d, and cells further than d are in the other are at the distance at least actually greater than d. Yeah? So you should only look inside these 8 cells, and there are at most 20, like 8 times 3, 24 points inside of these cells. So you check at most 24 points, and it works at 24n times. You must also take care how to organize these lists of points inside cells. This can be probably made using an ordered map from pair from int, which is the coordinate of the point of the cell, to vector of points. I don't know. This is always so something like that. Not that it is very light data structure, but it does its work. Our previous. So now the only question is, how do we find the distance? If we know how to find the answer, if we know the distance, but how to find the distance? Let's use the same idea as with this. Let's randomly shuffle our points and do the following. Initially, we consider the first 2 points to be the 2 closest ones. The distance between them is some t. So we create the grid and start our algorithm. We at the point and look at the 24, at most 24 points. Well, 27, yeah, because it's 27, 9 cells. 27 points in this 3 times 3 cells. If there is some point that is closer to us than a current t, then we make the refinement step. We replace d and start from the very beginning. We start. We drop all the points, and with the new d, we restart our flow. What is the probability that we will restart the algorithm at the step I? The probability is again 2 divided by limited from above by 2 divided by I, with the same argument as with mid disk, because for this to happen, we need the point number I be one of the 2 closest points among the first I, which happens with the probability of 2 divided by I. So with this probability, we will restart and again rearrange the first I points into the sums. So it is on average of the constant time of the steps. And the total number of steps is therefore the total complexity is on average linear. There is quite big constant in this OB because well, this is an upper limit. Of course, it's a rare case that there are so many points in every square number cell. Probably you can even refine, make a more precise upper bound for this number, like because there cannot be 3 points in every cell, because in this case points from neighboring cells will be too close, maybe, or something. So on average, I think this like 3 times 3 square, and at most something, I don't know, probably like 10 to 12 points, I think, but maybe a little bit more. It's a separate problem to calculate how many points you can fit there. But this algorithm, the previous algorithm that I have learned, the divide and conquer one, it also had an unpleasant like 7 coefficient, and it also had an algorithm n from divide and conquer. So probably this algorithm is still faster, and it's quite easy to code because to know the cell you just divide by d and round down the results. Very easy. Just be careful that d is floating point number actually, because it's the Euclidean distance here between the Cartesian distance between 2 points. So it's the floating point number. But the comparisons to refine d, they can be made in integers, like compare it to squares. So there generally be no problem. So this is another algorithm that uses the same argument, that randomly shuffling. Let's go to the general idea behind this method, and then we'll see another third algorithm that uses this method. The general idea is that if you're looking for some geometric, like extreme object, and this object only involves few points from the input, and you can easily check if the point belongs to the answer or no, and if it doesn't, then you don't do anything. Then randomly shuffling points initially gives you a low probability that the answer will be updated at each step, because the answer only involves few points, like 2 here or 3 here. And therefore, this random shuffle, this updating of the answer is rare, is a rare case, and for these rare cases, you can allow yourself linear number operations to make some global updates because of this answer refinement. So the third algorithm that I would like to present, well, it's actually one of the algorithms for the quite famous problem, which is half-place intersections. The half-plane intersection can be formulated as follows. Consider what is a half-plane. You have the line. For the line, you have the question. Sorry.
Question about the
Yeah.
How do you guarantee that you're only gonna reflect 27 distances if you're making the grid from D?
Again, you see, T is your known answer. You know that the answer is T. So if the answer is T, then there can be too many points inside any point. But if you already a new point, it can be closer than D, but in this case, it is also located inside one of these cells. Since before that, T was the answer before it and the new point. You know that before that, the invariant that each cell contains of all 3 points was satisfied. So now you have to look at most 27 points, actually usually less. But after that, if the answer is updated, you restart from the very beginning with the new D. So you drop all the current cell arrangement and start with the new D. And the random shuffle argument says that it has a low probability. So again, getting back to the half plane. Half plane, so consider the line. For this line, actually there are 2 sides. So the plane is divided by 2 sides. If we direct the line like this, so only check the normal. This is the left side or the right side, or this side and that side. This side where the normal is directed, and that side on the other. So what we want to find is we want to find we have a couple of these half planes, and we want to find. There are actually several stages of this problem. One, the simplest one, is there a point that belongs to all positive sides of all half planes? So, like here, we have like this triangle being the half plane intersection. So the answer is yes, there is such point. For example, should we have something like that? There is no such point. So no point that belongs to all the half planes simultaneously. The more complicated thing would be to find this point, so not only yes, no, but find some point with this property. And even more interesting would be to find the set of these points, described in some way. The set of these points, unfortunately, can have several possible structures. The most, it can be like half plane. If there is only one half plane, it can be infinite like this. So it can be infinite like this. It can be infinite even in the worst case, like two parallel lines making this stripe which has infinity to both sides. Or it can be a finite. In this case, it can be a polygon, it can be a segment, or it can be a symbol. So usually, for most applications in competitive programming, the infinite part is not important. So what we would do, and we would only consider such case that the answer is always finite. To ensure that this is the case, we will add the bounding box. We will add 4 very big very far half lengths, like max minus max. That will ensure that we are having the finite in half plane intersection. Actually, for many problems, you only want to know yes or no the point, not necessity to know this the form of the intersection. For example, if you are using this for some binary search, one example is the problem. You have like number of lines, and you want to find the point such that the most distant line is as close as possible. That was problem at our high school contest, maybe like several years ago. So the solution can be, so you binary search on the answer, and if you know the current, I will reuse the picture, so if you know the current D, the current candidate for the answer, you make a step at D from each of the given lines, and try to intersect all the stripes. Each stripe is given by 2 half lengths. So if it's empty, then this D is too small. If it's non-empty, then this D is okay. So you move back. R or L dependent. There can be other applications where you only need yes or no. At NIR, maybe a few years ago, at our non-duration, 3 years ago, we had the problem where also only the true or false was required. So, but sometimes you might want to calculate the area of that intersection or whatever, and in this case, you will need the full. We will now give the algorithm that finds the point in the intersection point. However, or the answer no if it doesn't exist. And this very algorithm that I will first tell you now is based on the same randomization idea. It cannot find the shape of the intersection. But after that, I will give you an algorithm which is better than that in both settings. It finds true or false for the point easier, and it can find the shape. But to give another example of the randomization method, I think this is also a good idea. So let's first solve the one-dimensional problem. So we have like the line, and we have half lines. So half line, intersection. How can we do that? Well, if the line is already has its coordinates, like so we have the coordinates x1, x2, x4. So we just looking from among the half lines that are directed in the positive direction, we choose the maximum start. From the half lines that are directed in the negative direction, we choose the minimum start. If they're like this, minimum negative is greater or equal than maximum positive. Then the intersection is not empty, and between those two, any point is okay. And actually, for half-line intersection, the answer is like the segment, and we have found the segment from here to here. So if it's the opposite is true, so if I have like some another half line pointing to the negative direction. So if this is so, then problem. Now, but what if the line? What if we have again one-dimensional problem, but the line is not the axis? The line is just the line, and the points and the directions are given in some other way. Then we can actually introduce the coordinate system of the line. How do we do that? We have the line given as the point and the direction vector. So the point will be the origin, so that will be 0. And the coordinate for the point Q that we all know that belongs to the line will be PQ scalar product to L. So we can divide it by the length of L, so that L is the unit vector. Or we cannot, because we cannot compare the values, so there is no actual need in absolute values. So this will be the coordinate on the line of the point Q on the line. L is like proportional to the unit vector. And we can actually, if we need, we can actually project some other point to this line within the same. This is exactly the projection, but if the point is already on the line, then no additional projection is needed. So this would be the coordinate on the line. So this is the way to introduce the coordinate system on the arbitrary line on the plane, and actually in the space if you need as well, but okay, we are on the plane. So, okay, and then how can we tell the direction? Again, if the direction is given by the vector, then by the vector d, then the sign of L dot d gives the direction. The positive sign means that the direction is positive in our sense of coordinate system, and the negative sign means that the direction is negative in the sense of our coordinate system introduced by this formula. So now we are fine with the one-dimensional problem. Let's go to the two-dimensional. How can we solve that? We will look for the extreme point in some sense. So, for example, we would like to find the point with the maximum y coordinate in the answer. That's actually only used to prove the complexity, and it works fine without that condition as well. But for the sake of complexity, for the sake of clarity of good complexity, we will find the extreme point, the topmost point of the intersection of the half planes. However, again, we don't need to find the topmost point. We can find any. The algorithm will work fine anyway. So initially we have this bounded box, and the topmost point is any point of the upper bound. This one, for example, max. So what are we gonna do? We add another half plane. If our point belongs to the correct side of the half plane, then we don't do anything. This point was the topmost point of the previous intersection and stays the topmost point of the new intersection. If this is not the case, if this point does not belong to the correct side of the half plane, then the similar argument to the previous two problems said that the topmost point of the answer must now belong to this, to the borderline of this half plane. Let's take this. Let's take all previous half planes that we have. Like in this particular picture, this are the 4 bounded boxes, but actually there can be some others that we have already confirmed. Let's intersect them with our line, and let's also project vectors to the to this line, and we would get the one-dimensional problem for our line. of finding the intersection. We'll have like this, and we'll also have like this, and so we will solve the one-dimensional problem, and from these 2 points, we will choose the upper one to keep the topmost point of the answer. Here I must say that it's not important actually, and in actual code you can choose any of these 2 points. The algorithm will continue correctly, and the complexity, at least heuristically, the complexity will not suffer anyway. But for the sake of correctness, we must take of complexity analysis, not take the topmost. So when we take the topmost point here and then continue. If or even on this line the intersection is empty, then definitely the total intersection of all half planes is also empty. So again, what is the probability that the topmost point of the answer belongs to the current line? The topmost point must be the vertex of the polygon that forms the intersection. This vertex has 2 lines that form that vertex. Actually, there can be more lines, but similar to the circle, actually, I didn't say about that. If there are 4 or more points, then the new point is never, further points never update the answer. They will already inside. So here, it is the same true here. More than 2 lines, only the first 2 lines update the answer, and the following will not update the answer. So the probability that the line should update the answer is therefore, as previously, T divided by I, and to solve one-dimensional problem we need I, and that gives the linear time algorithm again. But this algorithm, it answers true or false and finds 1 point inside the intersection. And it's based on the same idea. You must initially random shuffle all the lines except for the bounding box. It's better to start with the bounding box to have the specific point, initial point, because if you start without bounding box, the first steps are inconvenient because you have like infinitely far this point, this intersection, the far, and it's not convenient. So you add a lot of additional like cases to your solution. So these were 3 randomized algorithms that we have covered. Any questions or comments so far? If there are no questions, I will now give you a simpler way to find the intersection of the half planes, including the way to find the intersection itself, not only 1 point in it, or the is it empty or not. And also that algorithm, if you only need to find true or false for the point, it doesn't need to intersect lines. The funny thing is that this algorithm, it has to intersect lines to reduce the problem to 1 dimension. The funny thing about the next algorithm will be that it doesn't to intersect lines. However, if you need to find the polygon of the answer, of course you will need to intersect lines because its vertices are on the line intersection. So that's no way. Okay, so we have our half planes. Let's separately consider 3 classes of half planes. There will be half planes with vertical borders. Half planes with vertical borderlines are forming a separate 1-dimensional problem that we already know how to solve, and it's even a little bit easier than before because we don't need to project anything anywhere. They're vertical, so their x-coordinate is already aligned with our coordinate system. So simply take the maximum of x-coordinates for the half planes looking to the right, and the minimum of the x-coordinates of the half planes looking to the left, compare them, and either we have the segment of possible solutions for other planes, or we have maybe infinite if they're only looking to the left, only looking to the right. To avoid this, again, we use the bounding box. In this case, the left and the right parts of the bounding box guarantee that we don't have any infinities in the beginning. So, and also that there are no, that there are at least one, there's a please don't fire board. Okay.
Can you try to turn it off?
Alright, alright.
Back on. Just a second.
Turn it off, but it will. This one is out of but it was sleeping like several hours and then it decided to wake up. Okay. Interesting. I forgot what I was telling. Oh, I was telling about the half plane and section. Okay, so we have at least one. We fixed it. That one went out of control for some reason. What do we change? Okay, so at least one equation, right? At least one. Now let's deal with the other. The others, not vertical, are divided into classes. Looking down and looking up. So you may be tempted to build the upper hull and lower hull as we did in convex hull trick. This can be done, but not. But for the finding the intersection itself, maybe this is not such a good idea to do this. But for true or false or for one point, it can be much easier. It can be done much easier. Let's do the following. Let's look at the upper, at those guys looking down. So then there, let's introduce the function, call it f of x. That will be exactly that function from the yesterday's convex hull trick, the minimum value from among places looking down. From among half places looking down. Min looking down at point x. Select here, that y would be f of x. Let's introduce g of x as the maximum among looking up.
What's your microphone?
Not working? Working. Okay, again, let's introduce f of x as the minimum coordinate on the boards looking down. And g of x is the maximum looking up. So, if you say f of x is a convex, and g of x is concave, and if we make f of x minus g of x is concave, so minus g of x is convex as well, and the sum of two convex functions is convex, so this function is convex. Let's find the maximum of this function. If you remember 2 minutes ago, we have discussed that from our vertical half planes, we have limited ourselves to some segment from some L to some R. And we have the convex function f minus g at the whole line actually, in particular this segment. So let's find the maximum of this function on this segment. How do you find the maximum of the convex function? Ternary search, correct. To make a ternary search, you must evaluate this value, which is easy. You just use the definition. You find f of x using those. Looking down, you just put your x value, x1, x2, into all the equations of the planes looking down and looking up, and evaluate the corresponding value of y. There will be no division by 0 because we are not considering vertical planes or vertical borders, they were considered separate. So let's look at the how does the intersection look like. So we have like the upper half, we have, I will use another color, we have like the lower half. And the function, this difference, f minus g, it is actually looking like negative at the points where this halves intersect is 0. So it's negative, 0, positive, 0, and negative. Like convex function, its maximum corresponds to some position, some maximum vertical segment inside the answer. So you can use Turner's search to find this position x, and to find y, you have already evaluated a function of this position in Turner's search. So you know the topmost or the bottommost point at this position. And since it's maximum, it's actually at least one of them must be the intersection of the borderlands of the half planes, because if there are no intersections, either going or descending. So here it is. This algorithm doesn't use any geometry at all. It doesn't intersect any lines. It doesn't do anything except the ternary search. So the complexity is to evaluate this function. You need like consider all lines. It's for n. It's n times logarithm 1 divided by the precision epsilon. So this is the complexity. It is worse in complexity than the previous algorithm that we have discussed, the randomized one. It has on average the linear complexity. This one with this logarithm of precision, which for reasonable use, a programming combination is like 50. So it's like 10 to 12 times slower probably than that algorithm, but I don't think that you would be asked to intersect like 10 million planes, and if there are like 200,000 of them, then it should be fine. And the code here is much simpler. Now talking about the restoration of the answer, there are two options actually. You can either use the similar technique to convex half trick to create explicit upper and lower half, or you can start from this longest segment and go to the left and to the right again, but no, that will be similar. Convection maybe less precision. Maybe for restoring, yes, you need to find the lower half and the upper half. Find the point where they and use two pointers just to go along them. At some point they intersect, and at some point they intersect. But again, finding the polygon of intersection itself is a rare case. The more often case is to find true or false, or to find some point which can be solved using ternary search. Okay, questions so far? Comments? Then the final algorithm for today is Minkowski sum. What is the Minkowski sum? If you have two sets of points A and B, well, I will consider again the points on the plane, but you can generalize it to any reasonable vector space. So the Minkowski sum of A and B, A plus B, is the set of points X such that X is equal to A plus B, where A is in A and B is in B, like this. So this is called Minkowski sum. Let's start with some examples. For example, let's take a square and the circle. For example, let's make small circle and the square at the origin. How would you create the Minkowski sum of these two? So you would need to take any vector, and then all the shapes that I will be considering now are including their areas. So not only their border, but with the area. It can be also considered as the sum for the borders, but it's not convex, so it's more difficult to understand. So we will consider only, well, consider shapes including their inside. So we can take any point inside the square, any point inside the circle, and sum the corresponding vector. So this is similar, like you take the brush of the form of this circle and move its center so that you visit every point inside the square. What would you get? You would get like the square, and the circle goes around everywhere, so its extreme points must be in the corners, and it paints like everything around here. So this like square with rounded corners would be the Minkowski sum of the square and the circle. We will not be adding up squares and circles, we will be adding up polygons, and in particular convex polygons. So consider two convex polygons, for example, again. The square, let's see this one, and say a triangle like this. How would you add them up? Again, the intuition is the same. You take this triangular brush and the paint moving its center. This point, you see that this is attached to the coordinate system. So this is the center of this triangle. You move the center, the 0 point, anywhere inside this square, and what is painted, that is the Minkowski sum. So we will have like this. So again, we deduce that the extreme points are important, so we put this triangle with the central point at each corner, which vertex of our my painting abilities are not limited. I'm sorry. So like this, and you mentioned that it is just painting all around with this extreme position. So it's like something like that. See that it becomes like some distorted 7 gone. Has 7 vertices, like 1, 2, 3, 4, 5, 6, 7. Actually, 7 is not a random number here. How does 7 get from what we had? It's 4 plus 3. We had the square, which has 4 vertices, and then we had the triangular brush with 3 vertices. So it should not be such a big surprise that you were showing that there are 7 vertices as the result. polygon. So actually from this picture you can see how you can actually construct it in Kovsky some of two polygons. I will first tell the algorithm and then you will look closely at this picture and understand why it works. So the algorithm is very simple. Let's deconstruct our polygons that we want to sum into vectors. So they have, like in our case, we have like the edges of our square, this one, this one, this one, and this one. And for the triangle, we have its edges like, again, this one. Difficult to draw them outside of the triangle itself, like this one, this one, and that one. So I take these vectors, I decompose my polygons into their size, then I put them all in the same array and sort them by their polar angle. Remember, about 1 hour and a half ago, we were discussing that it's not such an easy problem to sort the set of vectors because of non-transitivity of comparator using only cross product. So you need to separately sort upper looking and down looking and combine them. Let's imagine we have done that, then what would be the answer? This, I guess that if we start from minus pi to pi, then not inclusive minus pi, then that would be 1. For the first one, then I take this one, then I take this one, yeah, then probably this one, then this, this, and this. So we sort all the sides of our polygons together, and then starting at some point, in this particular case at this one, we create, so this is like side number 1, then side number 2, then side number 3, side number 4, number 5, number 6, and number 7. So that is exactly what you do. Why is it correct? So imagine that you do the brush thing. So you do the brush of the form of one polygon and draw the answer, moving its center inside the center. Then it diverges us all those of the, I don't know, the polygon that is used at the canvas. You have the images of the polygon that you use as the brush. And if you want to like put some convex hull on it, then you have sides parallel to those, and between them, exactly the size of the brush polygon that fall into the corresponding answer. So that would be the result. It's not very formal, but I think it's enough to understand that the algorithm is correct, and the algorithm itself is very simple. The only thing that we need to take into account is that that we need to that coordinate system, because when we created these vectors separately, we created like our polygon was decomposed into the pieces. So at which position on the plane should we combine it? The answer is if you do it like this, so the minus pi not inclusive, the pi inclusive, then it's the position from which you start, like it's probably the topmost vertex of both polygons, and from those the rightmost. Yes, so the topmost and the rightmost. So you take the topmost and from among those the rightmost, add up their coordinates, and you get the starting position for your or leftmost, sorry, the most leftmost. So the topmost and the lowest leftmost, you start from that position, and you create that. That's important for some applications because sometimes, for example, if you're adding this one again, but the triangle is there, you get the result, but not here. If you imagine, this is again the brush, but the point at which you are holding this brush, it's outside of it, actually here. So you can imagine like the construction that has the brush here and like some needle here, then you move this needle all around this black one, creating this very thing, but not at the center here, but somewhere there. So it will be shifted by its topmost, leftmost coordinate. Okay, how can we use Minkowski sum? I will give you two applications, and that will be the final story, final two stories of our group.
I have a question. When you say shifted, is centering it in the origin?
You again, the same. So you draw the same, but starting at the point. You need what is the coordinate of this point? The coordinates of this point are this plus this. So when we were here, it was here. When we are like this will be shifted by this vector.
So you retracted that there.
Yes. So again, you are like if you're using this brush intuition, then the point that is walking around the canvas polygon in this case is the one the origin always. And the brush is somewhere there. It can be here, it can be there, and the result will be here or will be there. So the first task is to most distant points. Two most distant. There are many incorrect algorithms for this problem, so friend. You can try like some two-pointers approach, walking around the convex hull of the polygon, and fail with some incorrect word probability, but we have a chance of failing if you choose incorrect condition to move this pointer on that. So this, you should be very careful of that. But Minkowski sum allows you to solve this very easily. Let's see. So let's take the polygon. What we want to find. Well, again, first let's create the convex hull of the point. So the task is you have points of the plane, and you want to find two points that are at the maximal distance. The first thing you do, create the convex hull of the points. Definitely the answer belongs to the convex hull. The points are on the convex hull. Now, change this polygon, call it A. We want to find two most distant points in this polygon. They will be vertices, and vertices of the convex hull are our 0 points. So what I want to find? We want to find some x in A, y in A, such that the length of x minus y is max. Let's think. How can we find the x minus all points that are x minus y? Let's make the polygon minus A. How do we make this? We negate all the coordinates, but this operation is like a central symmetry with the origin. It also inverses the traversal from counterclockwise to clockwise, so it also reverses the traversal. So you reverse the order of the points along the polygon. Because algorithm for Minkowski sum, it needs, of course, those traversals be the same. So after you negate this, you take A minus A. The mathematical intuition said that it must be 0, but it's not. if you consider Minkowski as something like a plus minus a is the set that makes the definition of vectors x such that x is a plus b, where a belongs to a and b belongs to minus a, which is b belongs minus b belongs to a. So that is the set of all vectors x which are a minus b, for a and b belong to a. And this is the convex polygon. And what we, and if we want to find the maximal value, of course, it is at sum of its vertices. So just check this value for all of its vertices, and the vertex that corresponds to the maximum value of this length of the radius of this vector is the answer. If we want to find which particular vertices resulted in this maximal distance, we must go back to this, and we must remember actually which points from which sides of the original polygons this originated, and in this case that you when you go, so here this is this vertex plus this vertex. This, if you go along this, then the vertex of the black polygon doesn't change, and the vertex of the red polygon goes to the next node. This one is the next vertex of the red polygon, the same vertex of the black polygon. Then we go to the next vertex of the black polygon, and the same vertex of the red polygon, and so on. So if you take, in this sorting order, you take the vector from the red polygon, then each number of index of the vertex changes, and from the black polygon, its index of the vertex. Here the same, just the red one is the minus I and the black one is A, and so you can keep track of at which vertex of each polygon you are currently on, and this results in that you can find the correct answer. And the final task, actually quite similar, is distance between two polygons, two convex polygons. This may seem like a problem for some, I don't know, gradient method, some like descent, some like ternary storage, but actually Minkowski sum solves this without any numerical tricks. Again, you want to take a minus b, but this time you want minimum distance from the center, a minus b. And this will give you the minimum distance between two vertices. However, you must notice that the minimum distance is not always between the two vertices. It is also sometimes between a vertex and the side and the edge. How does it work in the Minkowski sum? The same way. We want to find the closest point in the Minkowski sum to the center, to the origin. It is not necessarily the vertex. It can be the side. So you iterate over. So like, let's draw the picture. There can be the case that this is the vertex, like this. Or there can be the case that this is the side, like this. So you need to have the function in, it's not as it is. This is a little bit more tricky, but still it works. It has, you just have to have the function of distance from the point to the center. This function can be implemented like take the minimum of the node. If you take the segment, you can always relax with the distance to its ends. It's never too bad. But the distance to the line of the segment should only be considered if the line intersects this segment. And that is if If projection is inside, that means that this angle and this angle are of different sides. Again, our favorite, or his favorite, cross product helps us to check. So this way you again know that the most important thing actually about Minkowski summits is its definition. From this definition, you see that you can find extreme points like maximal distance between the, for example, the polygon itself is the two most distant points. The closest distance between two polygons is the minimum to the origin. And for example, if the origin is inside the Minkowski sum, what does it mean? That the original polygons that we had range of interest. Okay, guys, we have survived for a week. Thank you very much for coming. Obrigado. Gracias.